Okay, so you are going to assume that you have purified your compound as of yesterday's experiment, and you are now going to analyze it. And the first of those two, let's talk about that vial that you left for gas chromatography as of yesterday's. Okay? To talk about chromatography, there are a vast number of different kinds of chromatography, and they all have the same features in that they have some kind of a stationary phase, they have some kind of a mobile phase, and they have some way of detecting how things move through that system in order to determine how many different components are present. And if you have run it with some standards, you are able to compare to standards of known material to determine an identity. So for gas chromatography, the stationary phase is the coating on the inside of a very fine capillary tube. It really looks like a wire to the eye. It's that thin. And it's coated with some kind of high boiling point liquid or with some kind of solid. There's a mobile phase, which is an inert gas that is moving through that tube, being blown through it. And the way that you are detecting how compounds behave in the system is that they're being injected, the entire system is heated so that the samples you inject are vaporized. And every time they're in vapor form, they're moving through the tube being pushed by that flowing gas. Okay? So this works well for volatile compounds. We know how it gets to the end of the tube by the fact it is burned as it comes off. That creates a signal that lets you know that something has come off, as well as how much of it, because the signal will be proportional to how much comes off. So we measure the different substances by how long it takes them to move through this particular system. Okay? So again, the system is a coil of capillary tubes, usually 30 meters worth of it, and it looks to eye like a fine copper wire. If we got a cross section and a close up of it, you'd see that it is coated on the inside with different kinds of materials depending on what you're trying to separate. And at the very end is this flame ionizer, and when it burns, it creates ionic charges that can carry a current to allow the detector to show that things are coming off. It only creates a current for organic compounds, so water does not work, and water is actually pretty detrimental to the system. So we make sure we put through just organic compounds. And this overall is what the system looks like. You would have seen it if you were in lab, that you would have set your sample up to be auto-injected into it. So the sample gets injected, it passes through that column, that coil, and out the other end. So using this from Mr. Farrar's lecture series, and you will probably see some of these slides if you look at his GC lecture. So I am borrowing these off of him. I want to give them that credit. The injection port is heated, so it's going to volatilize the sample. It's going to be injected in. This is just simplifying the way that the column looks. Okay. The carrier gas, we use nitrogen. It says most commonly helium, but we use nitrogen pushing through there. So every time that that substance is in the gas phase, it is getting pushed through the column. And that coating of oil and wax is there that may interact with your samples. Now, I'll say for what we work with, you do not have to be that concerned with the coating part. The samples are going to all act fairly similarly to that coating. So we're going to use another parameter that lets us predict how they are going to come out of this tubing, which we'll talk in a second. The entire thing is sunk down into an oven, so the entire thing is heated this whole time, keeping things in the vapor form. And at the end, the detector is going to detect that something comes out. So again, it can't identify it with what we've got. It just identifies that something comes out, and the more that comes out, the bigger the signal. So we're actually able to use it quantitatively. Okay. We record how the material comes through as retention time. So how many minutes does it take for the sample to make its way through the column? And there are a couple of things that are going to affect how long it takes to get through. The biggest one you want to focus on is the boiling point. So when it's boiling, it is going in equilibrium between condensing and vaporizing, condensing and vaporizing. So the more time it spends as vapor, the more time it can travel, because as a vapor, it's getting pushed through by the gas. So the lowest boiling point materials are going to come out the most quickly, and the higher boiling points will come out at a later time. And when you take a look at the standards for this experiment, just take a second and take a look at that and see how that's true with the set of 5 that we give you, that they're coming out in order of their boiling points. Now, they certainly do have an interaction with that coating on the inside of the column. It is picked for that reason. We just have a set that are all going to react fairly similarly, and the boiling points are enough to separate them for us to use that for identification. This is an example of what you might see for a gas chromatograph. You should at this point have yours, and you probably and hopefully are seeing just one single peak, letting you know you have just one compound. So when we're using it at the very end of a purification, most likely and hopefully you've got just one single peak, letting you know you have one single pure compound. This is an example of one that is a mixture, so there are multiple compounds present. And another thing that the instrument will do is calculate the percent of each one of those different peaks, different components that are in the mixture. So it adds together all the areas and finds out the percent of each that are there. You will see a similar table at the bottom of your chromatograph. And again, if you've got just one peak, you should be seeing just one single measurement for 100% because it should be pure. Okay? If you had more than one thing, you would see different kinds of percentages. You would see this whole array of data, even more than what is shown here in this example. The only 2 columns to pay attention to are the retention time in minutes, so there'll be a line for that, and the area percent over here. So if I was doing a synthesis and what I was interested in was the compound that I knew from comparison to a standard comes out at about 6 minutes, I'd say, okay, here's my 6-minute peak. That must be the stuff I want. Looks like my 6-minute peak is about 9.5% of this mixture. So there is one point later that you'll be using those percentages, but for the most part, again, you're using this as an assessment of purity. So focus on what information this GC is giving you. You know from the number of peaks the number of compounds. If it's just one, it's pure. If not, you can tell the percent purity by looking at that table at the bottom of the chromatograph. There will be a situation where we know we have multiple products and we'll be able to find the percent of each that way. The only way to use it for identification is you have to run a sample of a known sample of a particular compound through to find its retention time to compare to the retention time of your particular sample. So on As You Learn, you are going to be finding a pack that has each one of those possible unknown compounds run, and the retention time for each one of them will be shown on that graph as the peak that is shown there. There should also be a sample where all 5 are mixed together. It's a nice way to verify that all 5 of them coming out at distinctly different times, that we can tell one apart from the other, and that gives you a little more confidence in your identification. It also gives you a chance to look at that table beneath to look at the percent composition for each. So again, GC is going to give you an idea of purity, and in association with standards, it's going to let you know the identity of the compound that you have injected onto the chromatograph.